Okay, now that we know that a projectile's acceleration is just downwards at 9.8 meters per second squared, acceleration due to gravity, it then therefore becomes easy to describe the kinematics of a projectile. Okay, let me begin to develop the expressions for the kinematics of a projectile by setting it up in the following manner. Okay, here's two-dimensional space like so, x and y. Right here is our origin. Let's say that our projectile is launched from this position here like so with an initial velocity vector. The initial velocity vector is labeled as v0 like so. Its magnitude is the initial speed. Okay, now right here on the diagram is the initial position vector r0 of the projectile. I'm not going to draw, however, the vector itself, because if I did, that would then crowd up the diagram. Instead, what we draw are the components. Right here is the initial position horizontally, that's x0. Right here is the initial position vertically, that's y0, like so. Okay, now once again, take a look here at the initial velocity vector of the projectile. Its magnitude is the initial speed, v0, like so. And then let's examine the components, here and here. This right here is the component of the initial velocity vector horizontally. This is labeled as vx0. This right here is the initial component vertically. That's labeled as vy0. We also define an angle here on this diagram like so. This angle here called theta naught is referred to as the projection angle. Sometimes it's just referred to as the initial angle. Okay, and then let's say that sometime t goes by like so. The projectile moves along its path like so. And then right here at that instant at time t, it then has a velocity vector v that looks like this. Okay, now on the diagram, right here is the final position vector of the projectile. I'm not going to draw that vector. Instead, we draw its components. So right here is the final position horizontally. That's labeled as x. And then right here is the final position vertically. That's labeled as y. Okay, and then we have the velocity components here. Right here is the component of the velocity horizontally, v sub x. Right here is the component of the velocity vertically, v sub y. And now all that we do is we adapt the equations that we saw for the one-dimensional cases back in chapter 2, now for this two-dimensional case here in chapter 3. The reason why we can do that is because we already know what the acceleration is. It's just downwards at 9.8 meters per second squared. So for example, towards the end of chapter 2, we examined free fall kinematics. Those equations apply here as well. So for example, if you're talking about the position vertically of the projectile as a function of time, that's just written in the following manner. And then the velocity in the y direction here, that is vertically as a function of time, well, the equation that we already saw back for free fall in chapter 2, that also applies here as well. Like so. However, we do rename these equations slightly to take into account the two-dimensional case that we're talking about here in terms of a projectile. What we do in these expressions is we replace the vy0. Instead, we write the initial component of the velocity vy0 in terms of the initial speed and the projection angle. So for example, notice that vy0 here is just the opposite side of this little vector triangle. And recall that the opposite side is equal to the hypotenuse of the triangle, v0, the initial speed, multiplied by the sine of the angle. So then therefore, we replace the vy0 here in this term with the following. Like so. Take a look at this expression here carefully. This right here is the initial velocity component in the y direction, written in terms of the speed and the sine of the angle. Hypotenuse multiplied by the sine of the angle, like so. Okay, we do this also in the velocity expression as well. Specifically, we once again replace here the vy0 with hypotenuse multiplied by sine. Like so. Okay, so this describes position and velocity for a projectile vertically, but what about horizontally? Well, horizontally, I can begin to write the position and velocity equations in the following manner. Let me erase this from earlier. Okay, so horizontally, let's begin by writing the position equation in the following manner. Okay, notice this subscript X notation here when talking about the horizontal direction. However, keep in mind two things. Number one, the acceleration horizontally for a projectile is equal to 0. Recall that the acceleration is only downwards vertically at 9.8 meters per second squared. So this term here is equal to 0. We also replace the Vx naught in this term as well in the following manner. The Vx naught is right here on this diagram. This is the initial component of the velocity in the horizontal direction. We usually write this, the adjacent side of this triangle, in terms of the hypotenuse multiplied by the cosine of the angle. So then therefore the position equation horizontally for a projectile simplifies to become the following. Like so. And then once again, this term here is equal to 0 because there's no acceleration horizontally for a projectile. Okay, and then we have the velocity. Okay, the final velocity is equal to the initial velocity plus the acceleration multiplied by the time. But as I've already stated, this term here, the acceleration horizontally, is equal to 0 for a projectile. And as I did a few moments ago, we write the Vx naught here as being equal to the hypotenuse multiplied by the cosine of the angle in the little vector triangle on the diagram above. So then therefore you end up with the following. And this quantity here is a constant. It's a constant because recall that there is no acceleration horizontally for a projectile. The acceleration is only vertically downwards at 9.8 meters per second squared. So as the projectile moves through its trajectory, as we say, this component here of the velocity horizontally is the same as this component here. There is no acceleration horizontally for a projectile as it moves through its path. So to summarize then, we end up with 4 expressions. We end up with the vertical expressions there on the top board, and let me clean this up a little bit. These 2 expressions here that describe then what happens horizontally for a projectile. So these 4 expressions here are then therefore the kinematics equations of a projectile. And now we immediately begin to apply those equations with basic examples. Okay, what I'm going to do here is take a look at, first of all, the easiest possible case of a projectile. And as we examine this case here, I'm going to hopefully clear up some prior misconceptions that you may have had about projectile motion. Copy down the following problem into your notes. Let me go ahead and read it to you here. Okay, a bullet is fired horizontally at a height of 1.25 meters above the ground with a speed of 400 meters per second. In part A, when, where, and with what velocity does the bullet strike the ground? And then in part B, we're going to compare what happens to a ball that is initially dropped from rest at the exact same height as the exact same time that the gun is fired. We'll make a comparison in part B, but for now, let's just take a look at part A. Let me do some erasing. Okay, I'm also going to recopy up here for clarity my projectile kinematics equations. Okay, here's the vertical position once again. Here's the vertical velocity. Here's the horizontal position. And here's the horizontal velocity. Okay, now let's begin part A of this problem by drawing out a basic diagram. Okay, now just as we did when talking about one-dimensional free fall back in chapter 2, typically we tend to think of the ground as representing the vertical position, initially at least, as being equal to 0. In this case, however, the bullet is fired from a height of 1.25 meters. So we position that then above the origin, which is on the ground. So let's say that right here is the ground, like so. And then right here is where the bullet is fired. It's fired initially like so horizontally, such that the initial speed of the bullet here is given to us as 400 meters per second. By the way, this is a realistic number when talking about firing a weapon. It's a little bit above the speed of sound. Okay, now it does say that the bullet is fired horizontally. So then therefore, what is the projection angle theta naught equal to? It's equal to 0 because the projection angle is always measured with respect to the horizontal direction. Okay, and then we have the initial position. The initial position here vertically of the projectile is given to us. Why not? That's 1.25 meters above the ground. And then back in chapter 2, if you recall the horizontal situations that we looked at, typically we thought of the initial position horizontally as being equal to 0. Do the same thing here. So x naught is equal to 0. Okay, now the bullet is fired. Falls to the ground like so. And when it does reach the ground, it then at this instant has a final velocity vector v that we'll examine a little bit later on in the problem. And right here is v sub x. Right here is v sub y. Those components, v sub x and v sub y, are unknown. We're asked to calculate them here in part A of the example. Okay, we don't know how much time it takes for the bullet to fall to the ground in this manner, nor do we know what its final position is. We know that its final vertical position, y, is equal to 0 because it reaches ground level, but now with respect to the origin, right here in my diagram like so, this right here is the final position vector horizontally, this right here is x, and it's unknown. So notice that, as is always the case, I'm using the same methodology here for setting up and solving a physics problem, drawing out my diagram, writing down all of my knowns, and then writing down all of my unknowns. And then we have our relevant equations. We have our kinematics equations here for the projectile. Let's begin our analysis by taking a look at the first of these equations. Notice that in the first of these equations, two things are equal to 0. The final vertical position y is equal to 0, and the initial angle is equal to 0. Sine of 0 is equal to 0. So then therefore these two terms drop out in this vertical position equation, and the equation simplifies to become this. This looks familiar. We saw this equation back in chapter 2 for an object that was being dropped from rest. That is, for a one-dimensional free fall situation. We'll revisit that in part B of the problem in just a few minutes. But for now, if you take a look at this expression, which once again came from this expression here, notice that there is only one unknown, and that's the time t, which we can now solve for. So let's go ahead and solve for the time. So move the 1/2 gt squared here to the other side, like so. Okay, cross multiply the 2 and the g over to the other side, and then take the square root. When you do those couple of minor mathematical steps, you end up with this. And now at this point, I can go ahead and plug in all of my quantities. When I plug in for g, once again, we plug in the magnitude as 9.8 meters per second squared. The negative sign is already taken care of in the equations. So let's go ahead now and solve for the time. So I have here the square root of 2 times 1.25 meters. 1.25 meters, by the way, is about shoulder height. And then divide by g. And this works out to be about 1/2 second. Like so. So you take a rifle, for example, say like so, you aim exactly horizontally, and the bullet falls to the ground in only 1/2 second. Okay, now that I know this time, let's then go ahead and find its final horizontal position x by using this expression here. In this expression, there are once again a couple of zeros. The initial position horizontally is equal to 0, and then right here is the cosine of 0 degrees. The cosine of 0 degrees is equal to 1. So therefore, this equation here simplifies to become the following. Like so. So this is 400 meters per second multiplied by 1/2 second. This is the total distance here horizontally of 200 meters. So you fire the bullet horizontally, it falls to the ground in only 1/2 second, and horizontally it travels a distance here of 200 meters. Also in part A of the problem, it asks us to take a look at the details here of the velocity vector. So now let's go ahead and first of all find v sub y. We'll do so by using this expression here. In this expression, on the right-hand side of the expression, we have here the sine of 0 degrees, which is equal to 0. So then therefore, the equation v sub y becomes the following. Minus gt, which we've seen before. We saw that back in one-dimensional cases, back in chapter 2, once again for an object that was dropped from rest. We'll revisit that here in part B of the problem once again in just a few moments. But for now, let's go ahead and calculate this. So this is negative 9.8 and then multiply by a half a second. This is negative 4.9 meters per second. We also, however, have to find the horizontal component v sub x. That's found from here. However, in this expression, it is a constant, and on the right-hand side of the expression, we have here the cosine of 0 degrees. So then therefore, v sub x is equal to v naught. It's equal to 400 meters per second. Once again, there is no acceleration horizontally for a projectile. So then therefore, if you fire it horizontally, this x component here of 400 meters per second is the same as this x component here. That's also 400 meters per second. Therefore, in component form, we can now write the final velocity vector v of the projectile in the following way. Like so, where right here is the horizontal component, right here is the vertical component, like so. Notice that this vector points into the fourth quadrant. Positive x component, negative y component, exactly as we've drawn. If we wanted to find the final speed v of the projectile, we would use a little bit of Pythagorean theorem here with the sides of this right triangle. If we were asked to find this angle right here, we could do so by using a little bit of inverse tangent. However, it is not directly asked for here in this example. Okay, now let's take a look at part B. This is where we may clear up some prior misconceptions about projectiles that you may have had prior to today's lesson. Okay, let me move my file so I can read it. Okay, so now in part B it says, compared to a ball that is dropped from rest from the same height at the same time, which object would hit the ground first? Hopefully at this point you understand that both objects will hit the ground at the same time, but if not, let's take a look at part B in detail. Let's approach part B as if we would have done so back in chapter 2. Okay, so back in chapter 2, for one-dimensional free fall, we would have seen the equations, first of all, written in the following way. So here's the vertical position equation, and here's the vertical velocity equation, like so. And then back in chapter 2, we would have drawn out the problem in the following manner. Okay, so right here is the object and it's dropped from rest. The initial velocity vertically is equal to 0. Right here is the initial position vertically, y naught, equal to 1.25 meters. Okay, and then the object falls to the ground like so. It has a final vertical position y that's equal to 0. This takes place in an unknown amount of time t. And then right here is the final velocity v sub y, which is unknown. This is how we would have drawn out and approached this problem back in chapter 2. Okay, now let's immediately begin by taking a look at the position equation. In the position equation, two things are equal to 0. The final position and the initial velocity. So if these two terms are equal to 0, this equation then simplifies to become this. And then, as I said earlier, notice that this expression here is the exact same expression that we had ended up with earlier in part A of the problem when solving for the time t for the bullet being fired from the gun. Well, let's do the math here. Let's go ahead and move the 1/2 gt squared to the other side, like so. Cross multiply the 2 and the g over to the other side and then take the square root. In doing so, you end up with this expression here, which is the same as the equation above, and then therefore the times are the same. In half a second. So both objects hit the ground at the same time. Okay, let's go ahead and find the final velocity here, v sub y, as we would have done back in chapter 2. In order to do so, we'll use this expression here. In this expression, however, this term is equal to 0 because the ball is dropped from rest, and then therefore the equation simplifies to become this. Obviously the same thing is what we saw here for v sub y earlier in part A of the problem for the projectile. So this right here is negative 4.9 meters per second. Does this mean that the final speed of the two objects, the bullet in part A and the ball in part B, is the same? No, only the vertical component of the velocity is the same at negative 4.9 meters per second. The speed of the bullet at the end of the problem in part A would be found by doing Pythagorean theorem between these two numbers. it would be a little bit greater than 400 meters per second. However, in this case, for the ball that is dropped from rest, its final speed just prior to hitting the ground would be the magnitude here of 4.9 meters per second. But if you do fire the bullet horizontally, it does hit the ground at the same time as the ball that is dropped from rest. Think of this problem as like another version, if you will, of the monkey hunter demonstration. Think of the gun, for example, being aimed like so at the ball, which is over here. You then drop the ball and fire the gun at the same time, and then boom, the two objects hit right here at this point at the exact same time. Both objects are falling. They are both falling downwards at 9.8 meters per second squared. Okay, let me conclude this portion of this lecture here.